Okay, so we're going to talk about inverse functions. This is really not difficult. Again, you want to be really good at this because it is not difficult. And we start talking about inverse functions, we have to start off by talking about one-to-one functions. Okay, we've got to start with one-to-one functions right here. And often you'll see the notation 1-1. That's kind of the shorthanded way of writing a one-to-one function, making it easy. And it's pretty simple. A one-to-one function has to pass the horizontal line test. Okay, so if a function passes the vertical line, for it to be one-to-one, it has to also pass the horizontal line test. So if you can strike a horizontal line and only touch the graph in one place, then it is one-to-one. So the first one would be one-to-one because no matter where you put the horizontal line, you're not going to cross a point but one time. And then on the next example, of course, this one's trouble, right? That's a definite not one-to-one because you would hit the graph of the line several times. And then the last example is pretty good. Every time you draw a horizontal line, you would only cross it once, and so it is one-to-one. So they start with defining a one-to-one function because we're learning about inverses, and you can only have an inverse if your function is one-to-one. So we have to be one-to-one before we can have an inverse. So then they start talking about inverse functions, and they say if your function has an inverse, then when you perform the composition on them, the result better be x. If two functions are inverses of each other, when you perform the composition, you better equal x. So to prove that two functions are inverses of one another, we do the composition both directions, f composition g and g composition f, and they both have to algebraically turn out to equal x. So you'll see a question here that says, okay, you got a couple of functions here, are they inverses of one another? And the only way you can prove it is by performing the composition. So I need to do f composition g of x, which is f of g of x, which is f of 1/3 x minus 2. So that means go to the f function, and in place of the x value in the f function, put all that stuff that I have in that square bracket. So this becomes 3 times 1/3 x minus 2 plus 6. I'm going to have to move up a little bit. I can't fit it all on here, so I'm going to move up to another column. So this becomes 3 times 1/3 x minus 2, there's your x, plus 6. Well, 3 times a third is 1x, and 3 times a negative 2 is a negative 6. That's x minus 6 plus 6 on the end, so it works. Okay, it worked. It equaled x. The goal is to make sure that it equals x. Now I have to do it both directions. I also have to do the g composition f. I didn't give myself a whole lot of space here. So g composition f of x would be g of f of x, which would be, go to the g function now, and in place of the x in the g function, put f. Okay, so this is g of 3x plus 6, which is, go to the g function, is 1/3 times 3x plus 6 minus 2. 1/3 times 3 is x, and 1/3 times 2 is 6. Then you subtract 2 on the end, and once again, hey, it works. Okay, so if they both turn out to equal x, then you can say, yes, these functions are inverses of each other. Okay, so in the first example, they're definitely inverses of each other. We got it covered. So that one is, yes, they are. Now the second one, I hope I have enough room here. I really didn't give myself enough room here. So I think on the second one, I'm going to have to write a little bit higher on the page to fit it all in here. Okay, so I'm going to come up here. All right, so I need to go f of g of x, which is f in part B, f of the cube root of x plus 1. So in your second example, going to the f function, this little x here that I just highlighted is going to be replaced by the cube root of x plus 1. So this becomes the cube root of x plus 1 cubed minus 1. So the cube root cubed removes the radical and becomes x plus 1 minus 1, which is x. So it worked. Okay, it worked. When I did f composition g of x, it worked. But I have to do both of them. So to prove it, it looks like it's going to work, but to prove it, I have to do both of them. Now I have to do g of f of x and make sure it also equals x. So this is g of x cubed minus 1. So now I go to the g function, and in place of the x underneath the radical, I'm going to put that information that I have in the square brackets. So this becomes the cube root of, instead of x plus 1, x cubed plus 1. No, hold on, it's a minus 1. Hold on. X cubed minus 1. Then on the end is the plus 1. So this becomes the cube root of x cubed, which is x, and so it checks off. So these are inverses also. So you have to use a lot of algebra to prove when functions are inverses of each other. A lot of composition of functions. And when you do the composition, if the outcome is x plus 5, then they're not inverses. If the outcome is x, then you've landed it, and they are inverses. So both directions, both compositions, must equal x to prove that they are inverses of one another. Now, once you get the functions shown that they are inverses of each other, then the inverse is written, it looks kind of like an exponent of -1, but it's not. That is the symbol for an inverse of a function. You got that little -1 up there next to the f. That is the notation for an inverse. So you would say, you would rename the g of x as f inverse of x, if they're inverses of each other. Okay, so that's proving. I mean, somebody's giving you the functions. They just want you to algebraically see if they are inverses of each other. And in these two examples, they are. Okay, so where it really gets significant is you start looking at the graphs of a function and its inverse. So in number 3, it says graph the inverse of the function. The graph of the function is given, so graph the inverse. Okay, inverses are reflections, okay? F inverse of x is a reflection of f of x over the line y equaling x. So the inverse function is a reflection of the original function over the line y equaling x. All right, so where's the line y equaling x? The red line in your graph here, the red line in your graph is your y equaling x, okay? The red line is your y equaling x, or your dashed line since you're printed in black and white. That's that perfect line. That's that identity function that goes right through quadrant 1 and quadrant 3, splitting them exactly in half. Now, if the blue line, if our blue line is our f of x, then our inverse line must take that blue line and reflect it over the dashed y equaling x line. Okay, so if I reflect this one over, let's look at the bottom point. If I reflect this one over, it would end up being here, right? That would reflect it over it. Let's take the second point and see if we can bring it over. Take a diagonal through 2 of these squares, come back through a diagonal 2 squares, and it would be here. Okay, so take a diagonal about a 1 full 1.5 would be here. Here's my reflections, and my last one would be here. Those are my reflections over the line y equaling x. And so your reflection now, when you connect your dots, if I could draw straight lines, this would be a lot better, but this would be your reflection. So if f of x is the blue line, then reflecting it over y equaling x, the black line is the inverse function. Okay, so now let's make a little more fun with this. Okay, so my original function, let me list its points. This point, the first one I reflected, is at, quit that. Okay, the first one here is at, that lowest point is the point -4, -2, right? That's this point here. The next point, its ordered pair, would be at -3, +2. The next point is -1, +2. And the last point I reflected would be 1, 1, 2, 3, 4, would be 1, 4. So that's the points before I reflected them. Then when I reflected them to create the inverse function, when I did this, the point down low that I reflected, the first point I reflected, is now the point -2, -4. The second point that I reflected is the point 1 over down 3. Uh-oh, it should have been 2 over down. Wait. 1, 2, 3, 1, 1. Okay, hold on. I think I have a mistake here. I think this should be -3, 1. Let me go back to blue. Okay, so here we go. Let me fix this. All right, so now when I reflect it, it is 1, -3. And the next one is 2, -1. And my last point is 1, 2, 3, 4, up 1. So take a look at the way the points turn out. What happened to my ordered pairs? It just flipped them all, didn't it? Every ordered pair, the xy flipped. So when you reflect over the line y equaling x, you're going to exchange your x and y variables in every ordered point, every point on the line. Okay, that's pretty significant, very simple, very powerful pattern. Okay, very powerful pattern. Fun stuff. Okay. So now let's take a look and see what it says now. Okay, now they're going to ask me to find the equation of the inverse of the function. So far they've given both the function and the inverse and had me prove them. Then they gave me a graph of the original and had me graph the inverse and get some significance there. And now I'm supposed to start finding the equation myself. So to do that, it says replace f of x by y. Interchange your x and your y, solve for y, and rename it. Okay, well, let me do an example so that makes sense. Here's our example. Find the inverse of this function. So the first thing I'm going to do is I'm going to take it out of function notation. Okay, replace it, the f of x. Let's just start off by replacing the f of x with y and take the original function out of function notation. Now, to get my inverse, and I'm going to put a heading over here above it. To get my inverse function, I'm going to switch the x and y variables. So where there was a y, I put an x. And where there was an x, I put a y. So I switched the x and y variables just as the x and y values switched in the ordered pairs on the graph. The variables will switch algebraically. So I've interchanged the x and y variables, and now I need to solve for y. Okay, so in the blue over here, to solve for y, I'm going to first subtract 2, and then I need to multiply everything by 2 to get rid of the 1/2. So this will become 2x minus 4 equaling y. This is your inverse function. Your inverse function is 2x minus 4. So it's that simple. You simply switch out the ordered pairs to come up with the inverse function. Now my colors are so messed up here. But here is your inverse function, and here is your original function. Now, if you did the composition on both of these, you would get an algebraic result of just x. So now to graph these things, okay, if this point, if this is the point on the line, if it's negative 4, 0, the inverse function will go through 0, negative 4. If this is another point, which would be negative 2, positive 1, the inverse function would go through 1, negative 2. If this is the point 0, 2, the inverse will go through the point 2, 0. If this is another point, I'm just looking at the ones that I can name, 2, 3, then the inverse will go through 3, 2. See how this works? And it is so hard for me to draw a straight line. But, I think it looks something like this. This is your inverse function. There it is. I did pretty good. There it is. So, is that a reflection over the line y equaling x? Let me put y equaling x up here. This would be y equaling x. And yes, that is a reflection over that line, y equaling x. Okay, so every ordered pair switches, and the x and y variables switch in the equation. Okay, let's try another one. A one-to-one function is given. Write an equation for the inverse and graph it. Okay, so to write the inverse, first I'm going to take the original function out of function notation. So then when I'm ready to do my inverse function, I'm going to flip the x and y variables. So now this is x equaling y squared plus 5. Oh, it's a cubed. I'm sorry. Let me switch it out. It's a cubed. There we go. Okay, so I've got to solve it for y. So the first thing I do is I subtract the 5. And how do I get a cube off of the y? So I solve it for y. You take the cube root. Okay, and this is your inverse function. Okay, that is your function, your inverse function. So you have an original and you have an inverse. Okay, so I guess I can graph a few points and see if we can get this on here. So if I tried negative 1, negative 1 cubed is negative 1 plus 5 is 4. If I did 0, it would be 5. If I did 1, it would be 6. So this one would go through negative 1, 1, 2, 3, 4. Then we go through 0, 5, and 1, 6. Did I do that right? Yeah. Okay. And then 2 would be something huge, right? Be 8 plus 5, which would be way off the charts, 13. So really what it looks like, you remember what our cubed functions look like. They come up, angle through, and go up. That's what our cube function looks like. There's our original. Without even plugging points into my inverse function, I know that the table for my inverse function will be to reverse those ordered pairs. So my inverse function, without me plugging it into the equation at all, would be 4, negative 1, 5, 0, 6, 1, and 13, 2. Okay, 4, negative 1, 1, 2, 3, 4, negative 1, 5, 0, and 6, 1, and 13, 2 off the charts. So what would it look like? It would look something like that. So that's how they would look. So if you were to put in here the line y equaling x, they would be reflections over that line. Fun stuff. Okay, so here's your original equation. Here's your inverse. And there's your graphs. And I only found the ordered pairs on the original function. I just flipped them for the inverse. Just flip them for the inverse. Okay, so here's another one. Okay, let's take a look at this one. It says a one-to-one function is given. Write an equation for the inverse function and graph the inverse function. Compare domains and ranges. Okay, so here's my original function, y equaling x squared plus 3. And we know what it looks like. And they've got it sort of kind of graphed over here. But aren't we supposed to look like this? Doesn't an x squared function, isn't it the U shape? Okay, well, if it's a U shape, that sucker's not going to pass the horizontal line test and will not be one-to-one, which means it can't have an inverse. So what they do is they say, oh dear, we can't have the whole parabola because then it can't be one-to-one and it can't have an inverse, so we better only take half of it. We better limit ourselves to half of it. So then it will be one-to-one and it can have an inverse. And so that's why they put this stipulation in here of x greater than or equal to 0, because that just gives us half of the parabola, so it is therefore still one-to-one. Okay, so looking at this one, when they give me x greater than or equal to 0, that is telling me my domain. It says, hold on, we got to limit this thing so it'll be one-to-one. So the domain is where x is greater than or equal to 0, or the domain is 0 to infinity, which you can just look at the graph and see the domain is 0 to infinity. Still looking at the graph, what is the range on this thing? Looking at the graph, what is your lowest y value of this parabola? Positive 3 right here. This is your lowest y value, 0, 3. 3 to infinity. So that's your domain and your range of your original function. Again, the domain came from the fact that they told me that x would have to be greater than or equal to 0. That's where I got the domain. I had to limit my image. Okay, so now let's come over here and let's figure out what the inverse function is. Okay, the inverse function says take your original equation where y is, put x, and where x is, replace it with y. That's my inverse. Where there was x, put y. Where there was y, put x. Now solve it for y. So I subtract 3. And now I take the square root. But remember, when we take the square root, we're supposed to put a plus minus in front of it. Now, if I graph this, the square root of x minus 3, you know what the square root of x looks like? This is to the right 3. So 1, 2, 3, it's right here. And it should look something like that. But the plus minus in front of it puts the top part and the bottom part into the picture. That's the plus minus of the square root. So do I just have the top part, or do I just have the bottom part to be a reflection of the original function over the line y equaling x? Just the top part, right? Just the top part is going to be the reflection. So the inverse function is just the positive version of the radical. Just the positive, because the positive is the top half of that image. Okay, so it's just the positive. So now, looking at the black line graph, just looking at the graph, what is the domain? What is the first x value right here? Where does it start? What x value does it start with? 3, and it goes to infinity. What is your range? 0 to infinity. Very good. Very good. Now here's where it's got a neat connection. To find the equation, we flip the x and y. And what that does is it causes the range of the original to equal the domain of the inverse. and the domain of the original to equal the range of the inverse. So their domains and ranges also flip. Their x and y values flip, and their domains and ranges flip. Okay. Pretty cool stuff. Domain of the original equals the range of the inverse. The range of the original function equals the domain of the inverse. They switch just like the x and y variable switch, and that's just pretty important that you catch that. All right? Okay, so what's on my next page? Same kind of thing. A one-to-one function is given. Therefore, they're telling me you're good to go with an inverse if it's a one-to-one. Write the equation of the inverse and graph the inverse. Compare domains and ranges. Okay, so this is very similar to the other one. So I'm going to take it out of function notation. And then I'm going to talk about its domain. And I'm going to talk about its range because I'm going to flip them when I get the inverse function equation. Okay, so x squared minus 2, that's our x squared drop 2 unit, so it would look something like this. Well, that is not one-to-one. It won't pass the horizontal line test. So the domain is limited right here. It says where x is greater than or equal to -2, which is not a good setup. I don't have a good, that must be like a typo here. So let me change that to being x greater than or equal to 0. Make that a 0. Make that a 0. Okay, so that tells me my domain is from 0 to infinity. So in my graph now, I only get half of it. The left half has got to go, so I'm limiting my x values from 0 to infinity. So now it is one-to-one. Now I can legitimately find the inverse. From my graph, what is my range of my original function here? -2 to infinity. There we go. So we're good. All right, now let's go over here and figure out everything about the inverse function. All right, the inverse function means flip the variables from the original equation. So instead of y equaling x squared minus 2, it's x equaling y squared minus 2. That's the equation of the inverse function, but of course I need to solve it for y. Okay, so I'm going to add 2 to the left side. Oh boy, here comes the square root. The minute I write a square root, I have to put a plus minus in the front. Okay, the square root of x, we know what it looks like. The square root of x minus 2 means you move to the left 2 units. So you'd be over here looking something like this, right? Now if it's plus minus, I get the top and the bottom of the equation. But that doesn't work. Do I keep the top half of this or the bottom half of this equation, this graph, to be a reflection? It's the top half. So the bottom half goes, and that's the positive radical. So that means I only have the positive version of the square root. So it limits me to the top half of the graph. Okay, I can either look at my graph, this one, get the arrow, darn it, this one is my inverse function. Okay, that's my inverse. So now, from my inverse, I can either look at the graph or to find the domain and range, I can just switch them from the original function. So I can say the domain of my inverse is, oh yeah, it's the range of the original. So it must be -2 to infinity. The range of my inverse, I've been using RGE. The range of my inverse function would be the domain of my original. So it would have to be 0 to infinity. Now, looking at the graph of the inverse, is that correct? That that domain is from -2 to infinity and that range is from 0 to infinity? Does it confirm? Yes. Yeah, it does. Okay. Now again, I didn't do it last time, but don't forget, this is your line right here, your y equaling x, which I didn't get it perfect because I just rough drafted it. I just sketched it very lazily. But this is your line of reflection, y equaling x.
It looks like 0 for infinity.
Which one? The inverse function or the original?
Oh, sorry, I mixed it up. If I was looking at the x is greater than or equal to -2 or 0, I would change that one.
Right. Remember, the inverse function, the domain will equal, the domain of the original will be the range of the inverse, and the range of the original will be the domain of the inverse. They switch. Okay. They switch. And it confirms with the graph. Okay, it confirms with the graph. Pretty cool. And this one I think is a little more difficult. In fact, this one's kind of hard. This one's kind of hard. I debated about whether to even give y'all this one or not, but we'll try it, okay? All right, so the same question, let's take it out of this function notation. What a mess! Is that thing 1-to-1 in blue? And yeah, it is. Okay, it does pass the horizontal line test. It does. Okay, so let's take a look at the inverse and see if we can come up with the inverse. So the inverse would be x equaling 3y over y plus 1. How in the world do we solve this thing for y? Well, the first thing you want to do is go ahead and cross multiply. So kind of envision this x over a 1. So when you cross multiply, you're going to have x times y plus 1 equaling 1 times 3y. Now this is some important algebra I'm getting ready to do here. To get the y alone, you got to get the y out of the parentheses. So you go ahead and distribute the x here, and you're going to get an xy plus x equaling 3y. Now remember, your goal is for it to say y equals, because this is your f inverse of x. So now I need to get all the y's on the left side and the things that are not y's on the right. So I need to move the 3y to the left by subtracting it, and the x to the right by subtracting it. So I moved the 3y to the left and the x to the right. So I have the y variable on the left side of this equation. Now to get y alone, you're going to factor very simply. Y is like your GCF, leaving behind an x minus 3. So your last step to solve for y is to divide both sides by x minus 3. And so your inverse function is x over x minus 3. That is your inverse function. Now, graphing this was a little bit of a nightmare. Okay, graphing it was a little bit of a nightmare.
So wouldn't it be negative x?
Yeah, did I lose the negative? Yeah, I put the negative on there. Okay, graphing it is the pits. But what I did was I took and I created a table over here, and I picked some relatively good numbers. Like if x is -4, this would be a -12 over a -3, which is a +4. If x is -2, this would be -6 over -1, which is +6. If x is 0, it would be 0 over 1, which is 0. If x is 2, it would be 6 over 3, which is 2. And I didn't want to do 4 because that would be 12/5, so that's not good. I did 5, which was 5/5, which is even worse. Let's go ahead and do 4 then. 4 would be 12/5. Okay, so let's see if we can confirm the blue graph. -4, 4, yes. -2, 6, yes. The origin, yes. 2, 2, yes. And 4, that's an 8. So 1, 2, 3, 4. 12/5 is 2 2/5, so that looks pretty good. Okay, so we agree that that blue line is right, which is the original function. So my inverse function would have to go through the points, would have to go through those points switched. So instead of -4, 4, it'd be 4, -4, 6, -2, the origin, 2, 2, and then 12/5, 4. So we switch every ordered pair. And let's see what happens. So 4, -4, 1, 2, 3, 4, 1, 2, 3, 4, 6, -2, 5, 6, -2, then the origin. So this would be the lower part that would look something like this. So that's that reflection of that top quadrant. It's not exactly perfect. I could have arched it a little more, but that's about right. Then the origin, then 2, 2, and then 12/5, 4 would be 2 2/5, 1, 2, 2 2/5, 1, 2, 3, 4 here. And so this part would look something like this. There's your reflection. Okay. So you really have to plot. For me, that visual is kind of hard. So I have to plot points to be able to see that as a reflection over that line y equaling x. Okay, but it is. Okay, so just plot the points and try to get an image in your mind when you go in there and try to graph it. So that one's kind of hard. Okay, I will agree. That one's kind of tough. But at the same time, it's kind of fun. The algebra is the interesting part, and it really emphasizes the need to just switch the ordered pairs in the table to create your inverses graph. Okay, what's next? Come on, page, move. That's that the last page? Oh, wow. That's all we get to do? That is all we get to do. Are we early? Wow. Okay. Well, I'll close this recording.